Hello everyone. Welcome to our Ballerina Tech Talk on Ballerina meets GraalVM. In this Tech Talk, we will see how GraalVM empower the Ballerina cloud native applications. I am Dharmin Krishnandalingam, Senior Software Engineer at WSO2, and I'm excited to guide you through this Tech Talk. Let's get started. In this Tech Talk, I will be giving an overview of GraalVM, and we will go into a demo session where we build a GraalVM executable for a conference service application, and we will see how we can pack it in a Docker image as well. And finally, we will see how we can engage profiling and monitoring tools with a Ballerina GraalVM native executable. Without further delay, let's start with an overview of GraalVM. GraalVM is a high-performance cloud-native and polyglot JDK, which is designed to accelerate the execution of applications. This GraalVM has a different kind of distributions. There's a community edition, which is a free version of GraalVM. And there is also an enterprise edition, which is, of course, a paid version, which comes with a few additional features. And there is also a downstream distribution of the community edition, which is called as Mandrill, which is maintained by the Red Hat team. And recently, GraalVM community has also released an Oracle GraalVM, which is a distribution by Oracle, which is can be used for production and redistribution under the GraalVM free terms and condition license. So you can use either one of these GraalVM distribution with Ballerina to generate GraalVM native executables. So let's look at the GraalVM native image tool. So this GraalVM distribution has a high performance just-in-time compiler as well as a ahead-of-time compiler. So this ahead-of-time compiler is known as the GraalVM native image tool. So this is a technology to compile Java bytecode to ahead of time to create a platform-dependent binary, which we called as a native executable. So when we build a native executable, it does a static analysis to analyze the code and find all the reachable codes and use that fraction of resources to create the native executable. So due to this factor, this can be packed into a lightweight containers for faster and more efficient deployment. Also, it has a initial heap which stores the static object which are required to run the application. So because of this feature, the application can start in milliseconds and it can deliver peak and consistent performance immediately without warm-up. So these all performance improvements come with a cost, where the GraalVM native image build is a highly complicated process where they do a static analysis to find all the reachable code, and also they does a lot of optimization at the compiling phase as well. So this may consume a lot of memory and CPU, and it can result in an extended build time. Also, this GraalVM static analysis assumes a closed world assumption where the builder should know all the reachable codes at the build time. So due to this limitation, the Java's dynamic features such as reflection class loading are not directly supported. So in order to support such features, we have to configure them at the build time so that the builder knows which classes to be included in the final executable. So that is the brief overview of GraalVM and the GraalVM native image compiler. So let's look at how this GraalVM connects to our Ballerina story. So as you already know, Ballerina is a data-oriented language which has the first-class abstraction for network interactions, and it enriched with a lot of connectors. Because of this, Ballerina can simplify enterprise-grade cloud-native application development. On the other hand, we have GraalVM, which does an ahead-of-time compilation to produce a native executable, which can only use a low amount of memory footprint, which can achieve faster startup, and which can be packed into a compact container. So when a Ballerina meets GraalVM, we call it as a winning formula for cloud native applications, where the flexible, powerful, and the beautiful integrations with Ballerina can now achieve enhanced performance in the cloud using a GraalVM native executable. So without any more delay, let's look how we can build this GraalVM executable for a Ballerina application. So in order to build a GraalVM executable locally, you have to install Ballerina Swan Lake Update 7 or greater, where we announced our official support for GraalVM executables. And you have to install one of the GraalVM distributions, as I mentioned earlier. And you have to configure the GraalVM home environment variable. So that is the entry point where we use to find the native image tool. So in order to build the executable, we just have to run the build GraalVM command. So from that command, our Ballerina code will be compiled into a Java bytecode, and then GraalVM native image tool will convert that bytecode into a native executable. So as I mentioned earlier, it generates a platform-dependent executable, so it can only run on the machine we are building. But in the deployment and development stages, we are more concerned about building a native executable to a specific platform and pack it in a container. That is also possible with a core to cloud feature of Ballerina. So for that, you just have to run the build GraalVM with cloud Docker option. So this will build the native executable and it will pack it in a Docker image. So let's go into the demo and see how we can build a native executable locally and how we can pack it in a Docker image as well. So before starting, we have to install GraalVM. So you can visit their official site and go to the download page. And for this demo, I'm going to use the Ballerina Update 8 preview version. So that version supports Java 17. So you just have to download Java 17. So you can choose the platform here to download the distribution and install. Otherwise, you can also use SDK man to install. So you just have to copy this command and paste it in your terminal to install the Oracle GraalVM of Java 17. So that's just simple to install the GraalVM distribution in your machines. And then you have to set the GraalVM home environment variable. You can directly set it as the same as the Java home environment variable. So I have already installed native image and GraalVM. So can see the native image is running GraalVM Community Edition 17.08. And I have also set the GraalVM home to the same as the Java home, which is used by the SDK man. So now let's go to our conference service. So this is the service we are going to build today. So it has exposed three resources. One is to get conferences, and the second one is to create a conference resource, and the third one is to get conferences with country detail. So this conference service has connected to a in-memory H2 database. So where we store the conference data and retrieve the data. And it also connects to this country client, which will make request to the external country service to retrieve the country of the conferences. So when we make a request to the conference with country, it will retrieve the conference data from the H2 database. And for each conferences, we will make a request to this external country service and retrieve the country information. And then we will give the proper data back to our client. So that is the overview of the service we are going to build. So before going into the code, I'm just going to quickly run the GraalVM build since it will take some time to build. So we just have to use bal build with a GraalVM flag, and it will like compile our code into a Java bytecode, and it will start generating the GraalVM native image. So while it's building, I'll just explain the service here. So I'm just going to visualize it. So this is the overview diagram we have for the service. We have 3 resources here. If you go inside the conferences resource, we are returning an array of conference. The conference is a record which has an ID and name field. And then we have a post conferences resource, which accept a conference request as the payload. So the payload is just a JSON object with a name field. And when we create a conference resource, we are just returning a 201 created back to the client. And then we have this conferences with country resource, where we return an extended conference array as a return type. So this extended conference will have the name of the conference and the country of the conference. And we are just returning an array of this extended conference. So you can also go into the low code mode to see the interactions. So here we have the resource function on a do on fail. So we are making a resource call to this conference DB client. So this DB client will connect to the H2 database and retrieve the conference details. And for each conference, it will make a request to the country service to get the country details, and it will return the extended conference as an array here. So that array we are returning directly from here. So that is the overview of the service we have here. So let's check the status. Yeah, so we are nearly done. We are at the compiling stage. So you can see like the GraalVM native image build has some different steps. You can go to these links and check out the steps and what is done in this step. So this performing analysis is where the GraalVM finds all the reachable classes, and at compiling phase, it will convert the bytecode into the native binary, and it will write it to the target directory. So that is what going to happen in the build time. So when you are developing a Ballerina application using the Ballerina Lang, Ballerina standard library, and Ballerina extended modules, uh, it is guaranteed to give a proper GraalVM native image with an expected behavior. But sometimes if you have some third-party libraries, they might not be verified with GraalVM. So in that case, when you try to build with GraalVM, it will give you some warnings. So you can go through that warnings and contact those third-party libraries to check their status on GraalVM compatibility. So now we can see the image has been generated. So here you can see code area and image heap. as I mentioned earlier, the native image also has the code area as well as an initial heap where it stores all the static object requires to run this application. So that is what you are seeing here. You can also see the sizes of the image heap and the code area here. So the generated executable is in the target bin directory. So I'm just going to run it directly. Target bin conference service. So now you can see the service has been running. So let's do a quick testing. So I'm just going to send a post request with this conference. So you can see we are getting a 201 created. Now let's try to retrieve that conference. Here we are getting an array of conferences, and I'm going to add another conference as well. So it is also created. So I'll try to retrieve that as well. So now you can see both of these conferences here. So the native image is also working as expected. So now just stop this. And now we are going to build the native executable and pack it in a Docker image. So in order to do that, we have to pass the cloud equals Docker option here. So that will build the GraalVM executable uh, in a Docker image, and it will generate a Docker image containing that native executable. So as you can see, the building has started. So it will take some time to build the native image. So in the meantime, we can see the Docker file to understand what is going on here. So the Docker file is inside the target Docker directory. So this is the Docker file we have. So you can see it's a multi-stage Docker build where we build the native executable in one container, and we just pass it to a distillers container here. So we are using a GraalVM community edition image as a base image to build the native executable, and we are just running the native image command here. So one thing to notice is here we are passing this additional flag, which will generate a mostly static executable. So there are three type of linking when we come with the native executables. There's a dynamic linking and static linking, and there is this mostly static linking. So when we use the mostly static linking, it will link all the native libraries except the standard C library at the build time. So you don't need to install them in your container when you are running it. So when you are using a mostly static native executable, you can use a distillers base image to run the executable. You don't need to have any other libraries to run. So that is the default behavior, and you can even change the build image or the base image using a cloud.toml file. So you can configure the base image you want to build the native executable, and the base image you wanted to run this native executable as well. So let's check the status. Okay, so we are just inlining the methods. So it will take some time to build the Docker image. So now the compiling is done. Yes. Okay. Now the Docker image has been created. So I'm going to use a Docker compose file to run the conference service as well as a mock country service. So let me run Docker composer. Now the service has been started. Let's check the functionality. So I'm going to send a request here. Okay, that has been accepted and created. I can send this request to check all the conferences. And I can create another conference as well. So now I'm going to send a request to retrieve all conferences with the country detail. So now you can see we are getting the country detailed in the conference array. Uh, so just that's how we can build a native executable locally and how we can pack it in a Docker image as well. So we have also done a comparison between the JVM execution versus the GraalVM executable execution. So as you can see in the charts here, we have a significant improvement in the Docker image size, and the startup time is like 20 times 20 times reduced for a GraalVM executable. And the memory footprint is also like 1/3 of the memory footprint in the JVM execution. So we sacrifice the compile time and we obtain a smaller size images with better startup time and memory footprint due to the GraalVM executable. So now let's look at how we can engage profiling and monitoring tools with the Ballerina GraalVM executable. So this is already supported in GraalVM native image. So in this session, we are going to look how we can integrate that with a Ballerina GraalVM executable. So we will first look at how we can generate heap dumps. So in order to generate heapdumps, we just have to pass dash dash enable monitoring equals heapdump option. So this option should be passed to the native image builder. So the additional options we need to pass to the native image builder, we can pass it using the GraalVM build options flag. So these all these options will be appended to the native image build command so that it can enable monitoring using heap dumps. And currently there are 3 different ways to generate heap dumps for a GraalVM executable. The first one is to create heap dumps by sending a user specified user defined signal at the runtime. And then the second option is to dump the initial heap of the image using a runtime option. So this might be helpful if you want to inspect what is there in the initial heap of a native executable. And the third option is to create heap dumps using the visual VM, just like we create for a Java process. So in order to enable that, we just have to pass enable monitoring with JVM stat as well. So from that option, the native image process will be shown in the visual VM UI so that you can directly get heap dumps from that. And the second topic is to connect to a Java flight recorder. So this is also possible by passing JFR as an option to the enable monitoring flag. So when we pass this option, we can see some runtime arguments available in the native executable, where we can enable and start a recording, and we can even configure locking at the runtime as well. So these options are only available only when we build the GraalVM native executable with this specific option. So now let's go back to our demo application and see how we can enable this monitoring with the Ballerina GraalVM executable. Okay, so we just have to run build with GraalVM. We have to pass additional build options as GraalVM build options, and that should be enable monitoring. So I'm going to enable all three: Heapdump, JVM stat, and JFR. So from this option, we are enabling Heapdump, and we are also making it available as a JVM process, and we are also enabling JFR as well. So while it's building, I'll just explain the runtime options of a GraalVM executable. So I have already built an image here in the native in directory. So this image is created without the monitoring support. So we can run native in conference. So for example, if you want to define the max heap size for this process, you can just pass xmx 1g just like a Java process. So this will start the process with the 1 GB max heap size. So in order to find all the options, you can pass a print flags option. So it will print all the possible options with this particular GraalVM executable. Since I haven't enabled monitoring in this native executable, you might not see anything related to JFR here. So when our native executable is ready, we can check the build option there as well. So yes, so it's compiling. Let's wait for some times to make this build succeed. It will take some time to build. So that is the only disadvantage here. Okay, now the compiling phase is done. Okay, now the image has been generated. So let's first check uh, the runtime option available with this image. So here you can see there's option to enable flight recorder and define the flight recorder locking. And also you can see we can start a flight recording option as well. So these runtime options will be only available if we build the native executable with that build command. So let's try to run this by enabling the flight recorder. Okay, so now the application is running. So we can just check by sending pause request and getting it back. Yeah, it seems to be working. So now let's look at how we can create a heap dump for this process. So I'm just going to send a user defined signal to this process. So I'll just take the process ID and I'm going to send the user defined signal to this process ID. So you can see there's no change in the running application and it works as expected. But if you see here, you can see the heap dump has been created with a timestamp here. So that is how you can create a heap dump using the by sending the user defined signal to the process. And let's open Visual VM and see whether this process is available here. So this Ballerina conference service is available in here. So you can see the resources here. I'll just send some other request. Okay, it seems to be working. And you can see some increase here. And you can just generate heap dumps just like JVM process. So you can create heap dumps here. So it will generate the heap dump for you. And you can also check the JFR using the JDK emission control. So here also you can see this Ballerina conference service and flight recorder here. And you can also generate heap dumps here. Just put some name here. So it will generate the heap dump without affecting the functionality. So you can see still the process is running and we can even make requests. So yes, that's how we can connect a flight recorder with a GraalVM native executable and how we can generate heap dumps with a Ballerina GraalVM executable. So let's go back to the slide. So yeah, that's all for this tech talk. If you want to find out more, you can always refer to our Ballerina Learn guides we have in our website. And you can also join the Ballerina community through Twitter. You can follow up our articles on Stack Overflow collectives. And if you have any questions, you can always uh, ask in the Discord or create GitHub issues. So it's time for questions. I'm happy to answer any of your questions. Okay, I see a question. Okay, can you generate a Docker image from a Scratch container instead of distillers? Yes, we can. We have to build a statically linked native executable in that uh, sense, but it's not ensured to be working. So you can refer to the GraalVM guides. You have to link it with the muscle and use their container to build it. So it is possible, uh, but we haven't verified the performance with the Scratch images.
Hi, Karmikan. There is another question by Sahara.
Okay.
Does
Mm,
Ballerina?
So I can give it a try to answer that question. There was a similar question in Discord channel a few days ago as well. So Ballerina does not support actor model directly, but you can implement a similar functionality using workers and inter-worker message passing features in the language. You can build something similar to actor model. Our concurrency is also based on strands. Like strands are like lightweight thread, just like Go routines and Kotlin coroutines. That model is similar. And then inside the function, you can create something like workers where you can organize your code in multiple code blocks, and those code blocks can run in parallel, right? That's a worker, and each worker can send messages to the other worker. There's a inherent channel between one worker to the another, so you can interact with these workers using um, uh, worker to worker channels. Um, so we don't fully support actor model, but you can do something similar. We can publish some more information on that later. Hope that answers the question.
So if there is no other questions, we can wind up the session. So thank you all for joining. I hope you have a great time exploring GraalVM with Ballerina. And if you have any more questions, please raise them in our Ballerina Discord server. Thank you for joining again. Have a great day.